All right, in this example, we're going to look at a technique of integration, commonly referred to as U-Substitution or change of variable. If you look at the function we need to integrate, 9x times the square root of 3x squared minus 5, it seems a bit complicated. Okay, so what we want to do is make it easier. All right, so typically, most of the time, if you let U-Substitution be the input function to our composite function, if you'll notice here, really what we have is a composite function, okay, and multiplied by something pretty close to the derivative of the input of that composite, okay. That should sound familiar. That should sound a lot like the chain rule. Remember when we did the chain rule, when we took derivatives, right? We took the derivative of the outside piece and then multiplied by the derivative of the input function, okay. We were dealing with composite functions then as well. So you'll notice I have a composite function, the square root of 3x squared minus 5, multiplied almost by the derivative of the input. Okay? So the technique here, most of the time when we do U-Substitution, we're going to let U be the input function, in this case, the 3x squared minus 5. Okay? So if I'm going to replace this with U, then I can't have x's anymore. I also have to substitute those out. Okay, so I can't have a dx here. What I need is a du if I'm going to write this function in terms of u. So here's how we can do that. We differentiate, okay, using our differential. The differential of u is 6x dx, and I can solve that for dx by dividing by 6x. Okay, so this is kind of, maybe put this in a box, kind of come over to the side and do that, and then go back and substitute over here and make this an interval over u. Okay, we're going to integrate over u instead of x. So let's see what we can do with that. So according to this relationship between u and x, I have the interval. I guess I'll leave my 9x here, right, and I'll replace that with u. So it's the square root of u, which is the same thing as u to the 1/2, right? Because that's u, square root of u, or u to the 1/2. And then dx I know is du over 6x. Okay? So what happens here, x divided by x, that's convenient, right? Because those x's cancel out, and now I don't have any x's left, so that's a good sign. What I can do is pull this fraction out, 9 over 6, or 3 over 2, using my constant multiple property for integrals, and then that leaves me with u to the 1/2 du. Okay, which is a fairly easy function to integrate, right? We've dealt with these before. I've reduced something that seemed quite complicated to a nice easy interval. Okay, so now what I do is integrate, find the antiderivative of u to the 1/2. So the constant stays there. What do I do with this piece? Of course I add 1 to the power and then divide by my new power, right? So divide by 3/2 or multiply by 2/3, okay? And in this case, conveniently, my coefficient's gone, so I end up with u to the 3/2. I forgot my constant of integration plus c. So I get u to the 3/2 plus c, and now I'm almost done. If I want to integrate a function of x, I should end up with a function of x. I got to go back and back substitute, and I should get 3x squared minus 5 to the 3/2 plus c. Okay? And that is my antiderivative. I can always check that by differentiating this, right? If I differentiate this, I should of course end up with this original function. So think about what happens there. I get pull down the 3/2, leave that alone, take 1 away. 3/2 times 3x squared minus 5 to the 1/2, and then multiply by the input function derivative, which would be 6x, okay? And then I should end up with 9x times that. Okay, so you can always check by taking the derivative of your answer for your interval to see if you get your original function. Okay, let's do one more. Sine squared 3x times cosine 3x, the integral of that. How am I going to do that? The same way. I need to figure out what my input function is going to be. In this case, it's not quite as clear as the last example, at least I don't think it is. I have two input functions, really a composite of a composite. This is the sine function being squared, so you can think of your sine function as an input, and then I have a 3x as an input function as well, right? If you let u be 3x, you're not going to get very far, right? It's just a multiple of x, so you're a constant multiple of x, so it's not going to get you very far if you do substitution. So what I'm going to try and do is first rewrite it, just to show you that I do in fact have a composite function. Right? This notation is used with the trigonometric functions. Instead of squaring the whole thing, it's just put in a different place. So it helps me a little bit if I write it like that. That's the sine of 3x quantity squared. I can see a little bit more clear that that's a composite function, right? So in a way, it's kind of guiding me towards what I'm going to use for u, right? And sometimes with these, you try one thing, it doesn't work, so you try something else. But I'll come over here and let the sine of 3x be u, all right? And then take the derivative. Cosine 3x times 3 dx, that's my chain rule, okay? So if I solve that for dx, I get du over 3 cosine 3x, okay? Use that to substitute. Sine 3x squared is just u squared, right? Because we let u be sine 3x. And now, times cosine 3x, that guy's still there. Dx, which we know is du over 3 cosine 3x. Okay, so that looks a little funny because I got x's and u's, but what's going to happen in this case, as in most of these examples, is my cosine 3x, or the piece of this integral that still has an x in it, goes away, right? It cancels out. So I end up with a fairly easy integral. Once again, bring out the 1/3, and I only have to integrate u squared du, which I know how to do, right? I can simply add 3 to that, or add 1 to this, and divide by that new power. So what I'm going to do is, I'm running out of room, come up here to finish. Okay, so we took a fairly complicated function of x integrated, changed it to a function of u with some substitution, recognizing a relationship there with the sine squared of 3x and the cosine of 3x, substitute, and now I can integrate this piece, add 3, or add 1 to the power and divide by the new power, plus my constant of integration. And then I go back and substitute for u, right? U is sine 3x. Okay, and I get my integral. Remember, we were integrating a function of x, so I should end up with a function of x, so I don't want to stop there. Right, I got to go back substitute for my function of x. Okay, there's just a couple examples with U-substitution. You need to do a lot of practice with those in order to get it down. Okay, so keep working on your homework.